In this video, we're going to look at how to combine our knowledge of multi-step chemical reactions with writing potential energy curves. So if we take a look at these three elementary processes here, each of these are the three different steps involved with an organic substitution reaction where we take a Cl ion and remove it from this hydrocarbon here, replacing it with a water molecule, which takes three individual steps. Now, basically what we would do is we would write the potential energy curves for each of the individual elementary processes that we have here and string them together so that each of them connects with the previous step and forms an overall potential energy curve that looks like this. Now we can see, because there are three individual steps to this reaction, that means that the reaction is going to have three different peaks, and as we know from the mechanism on a potential energy curve, that each of these peaks represents an activated complex. Remember that an activated complex is the unstable structure that is formed when the reactants collide with each other. So in the first case, the activated complex is a little bit weird because this is effectively a decomposition reaction, but the activated complex here would be where the bond is neither a bond nor a lone pair, but is in the process of breaking in order to give us our products. Here in step 2, the activated complex is when water collides with this positively charged carbon here, and in our final reaction, the activated complex is where one water molecule is colliding with the hydrogen here and removing it, which would give us our final product. Now we can see, based on the shape of each potential energy curve, that we can draw EA, the activation energy, and delta H, the energy change between reactants and products for each individual reaction. So in reaction 1, this is the activation energy between the reactants and the activated complex, so we can call this EA1, and if we measure the distance between products and reactants of step 1, this would be delta H1. Likewise, for reaction 2, we can write in EA2 right here, and if we measure the distance between reactants and products, we can find that our delta H of the second reaction is here, and finally the distance between the activated complex and the reactants of reaction 3 is our EA3, and we can see the final delta H value is here. Now we know from Hess's law that if we wanted to calculate what the overall delta H would be, all that we would need to do is add the individual delta H values together, and it should give us the overall delta H value. However, we don't actually need to do that if we're looking at a potential energy curve like this. We can simply find the overall delta H value by looking at the overall potential energy of the final products of the reaction, which would be here at the end of step 3, and simply subtract from that the overall potential energy of the reactants at the beginning of step 1. And if we draw a dotted line to show where our starting potential energy is, we can draw a value for our delta H overall, again representing the overall energy change from the original reactants in step 1 to the final products at the end of step 3. Where it comes to calculating the overall EA, this is a little bit different. The temptation would be to take the activation energy for each step and add them together the same way we could do with delta H. However, this doesn't actually make any sense because we can see that step 1 here has a significantly larger activation energy than the activation energy of step 2 and 3. What this means is that if we get enough kinetic energy input in step 1, that amount of energy, because it's greater than the activation energies in step 2 and 3, this amount of energy to get to step 1 would be enough to complete the overall reaction because it's significantly greater than the activation energy required for step 2 and 3. So to find the overall activation energy of a multi-step reaction, it's actually fairly straightforward. All that we would need to do is to look for the largest EA value of each of the individual steps, because once again, if we have enough energy to get through step 1, that same energy can be used to give the reaction momentum to overcome the activation energies in step 2 and 3. Now, for that reason, the step with the highest activation energy, in this case step 1, is what we call the rate determining step. We call it the rate determining step because once we have enough energy to overcome this EA barrier and successfully do reaction number 1, the other 2 reactions will happen fairly spontaneously. So because this reaction requires the most energy to start, this is also going to be the slowest step that occurs in the reaction because it requires the largest energy input in order to overcome. In the next video, we are going to expand on this notion of multi-step potential energy curves by looking at how catalysts influence the overall process of a chemical reaction with respect to potential energy.